Okay, so I feel like in the last few lectures, there's been a few times, it seems louder than normal, yeah? How's that? Yeah? There's been a few times where I wrote something on the board or showed something on the slide, and I said, okay, but that's a disjunctive constraint, an or constraint. You know, that's a hard sort of discrete combinatorial type of constraint. So we'll cover that in a future lecture, right? Well, today is the lecture where we're going to start to work through some of that. And some of you are using GCS, for instance, graph of convex sets, for your project. So this will be you'll hopefully understand that better by the end of the lecture. Okay, so I have a couple slides that I'll start with, but I'll do a lot of it on the board too. So the first example that we came across throughout the lectures of sort of hard, difficult non-convexity in the motion planning problem was just if you're doing obstacle avoidance, right? So let's say we're going to go from the start to the goal, and we have to plan a path, and clearly there's both discrete aspects of the problem, right? We have to decide if we're going to go left or right, and there's also continuous aspects of the problem, because we have to decide, once we decide to go left, conditioned on the idea if we're going to go left or right, then we have to choose a smooth path that goes around that. It satisfies dynamic constraints, velocity constraints, whatever. Okay, so I said discrete, but I've also said combinatorial, right? So the point is, when you have one obstacle, then you have just one choice, roughly. You're going to go left or right. That doesn't sound too bad. Okay, but if you suddenly find yourself in a forest or in a maze or something like this, then making that discrete choice, all the times leads to a combinatorial number of possible discrete decisions. Okay, so if you're not careful, that can be very bad for your nonlinear trajectory optimizer, right? Now, if you, from the other perspective, if it's a purely discrete problem, if you were to just say, make a point on a graph and just do graph search to find a path through a maze, then that's like no problem whatsoever. We know how to do graph search. That's easy. But if you say I want to fly a quadrotor through this and subject the path to the constraints of the quadrotor and avoid collisions and stuff like this, then suddenly that seems like an astronomically hard problem that we haven't got good solutions for. Okay, so the goal is to try to bring these two tool chains, discrete planning, which is very powerful, can solve big problems, continuous trajectory optimization, that we can solve smooth problems but doesn't handle these discrete instances very well, and try to bring them together. Yeah? Okay, so let's work through a couple different transcriptions. So the simplest way to sort of write down this problem would be to have, I could call it Q, call it X, okay? 1 point for every not point on the trajectory. I'm going to have a fixed number of X's, okay? I don't even have dynamics here. Let's just say I want to find a continuous path, okay? I'll minimize something like the squared distance between the points, just to somehow a sense of distance. That's actually a little weird one. I don't like having the squared distance. I like the distance. But this is fine. This is more like our LQR problems, okay? The initial conditions are at the start. The final conditions are at the goal. And then somehow we have to write the collision avoidance constraints. We've been saying before, the general tool for that is min-distance constraint, implemented cleverly with a collision engine in Drake. In this case, we can write it very simply. I chose this to be the obstacle basically to be in X1, X2 to basically just be the L1 ball, right? So we have I wrote the obstacle like this. Of course, you could transform that, move that, and write something similar. But if your obstacle just happens to be there, then you can write the constraint super simply. You just say that the L1 norm of X has to be greater than 1, okay? Now that's a non-convex constraint as written. That's the, be outside the collision, the L1 ball, okay? It's non-convex. that means SNOPT is going to do its best, okay, but it's going to have local minima. And I'm going to have my running notebook here, okay, of all these different transcriptions that we'll step through. Okay, so the first version of this is just the nonlinear trajectory optimization. Okay, and I'm going to solve the problem using the previous solution as the initial guess. Okay, and so it's found some solution. That's great. But if I move the initial conditions or final conditions around, okay, then it keeps solving. That's fine. And the problem, of course, is that there's local minima. If I move it over here, then there's nothing that will do. If it started considering the right around the goal, then it's never going to snap over to the left around the goal, because this point, for instance, has to violate a constraint before it can come around to the other side. So this is our classic local minima problem. Okay, so how are we going to make that better? We're going to start leveraging tools from discrete optimization. One way to do it is to write explicitly disjunctive constraints, okay? So this is a reasonable constraint. I could say that I'm in this region over here. So xn is strictly, xn is strictly outside of this face. That's a convex constraint. But of course, not all of the points on my trajectory are going to be able to satisfy that constraint. The initial condition doesn't satisfy that constraint. But I could write another constraint for this face, another constraint for this face, another constraint for this face, and then somehow I want to write my constraint to the optimizer as, for every n, pick, you either need to satisfy this constraint, or this constraint, or this constraint, or this constraint, right? At least one of those. So how do you write that to the optimizer? Okay, there's a couple different ways to do it. There's kind of a recipe of different ways to write disjunctive constraints, this is called. I'll take a simple example of it. If I want to say cx1, or I just made a scalar version of the constraint. Okay. If you want to send this to an optimizer, then one way to transcribe it is to use mixed integer programming. Okay. Or even mixed integer convex programming. So we'll mostly lean on today, which is MICP sometimes, affectionately called. Okay. The idea would be that you're going to introduce a new variable, a binary variable. Okay. Maybe just to make it simple, I'll add 2. Okay, when I say it's a binary variable, that means what I mean is that it can only take values 0 or 1. Okay? Maybe not surprisingly, once you give the optimizer the ability to sort of make one discrete choice, this or this, okay, then you can sort of transcribe more complicated equations so that you can write this by leveraging the or that exists just on the binary variables. It's kind of compressing all of the disjunctions into just the b variable, and then having a solver that knows how to sort of search the b variables. Okay? There's a couple different ways to do that transcription. One of the simplest ones to understand is the big M formulations. So how would that look? That would look something like C1 transpose X less than or equal to D1 plus B1 times M. M is literally just a big positive number. Okay, and then I'll say C2 of X, D2 plus B2 of M. B has got to be either 0 or 1. Okay? And then if you want to make sure that at least one of them is on, then you want to say, for instance, that the sum of BIs is going to be greater than or equal to 1. At least one of these B's must be 1. Maybe I wrote that backwards. I probably want that to be 1 minus B here, if I want that to be this. At least one of them has to be on, which means this is inactive. Let me fix that. You can either use B or 1 minus B and choose between the 1 or the 0, but it's slightly cleaner in this one to just do this. Okay, so what's the idea here? Let's look at this one here. Okay, so I've said that my points have to be over somewhere in this set here. Okay, so when I take the dot product of x with the vector 1, 1, it has to be greater than 1. If I say then that plus, or geez, did I get the sign wrong again too? No, that's okay. I just have I used greater than here and less than there. Okay, but basically, if I can modify this to be either this exactly, if B is 1 in this case, if B is 1, this is 0, and this term contributes nothing. So my original constraint is active. Okay. Right? If B is 0, then this is 1, and what does that do? That effectively takes this constraint and moves it away here so that it's not impacting the solution. Right? It's just moving the bound sort of till it's vacuous. That's why it's some positive big number. You know, as long as it's sort of bigger than all the variables you care about in the problem, then that's fine. You don't want to make it super big because then you'll get the numerical issues for your solver, okay? But just enough that it kind of gets out of the way. And you can do that for all of those. But if you write a constraint saying that the sum of B's is greater than or equal to 1, that means at least one of the B's has to be active. Okay, so at least one of those constraints has to be satisfied. And that's just a way to use the OR capabilities of the binary variables to write like linear constraints. Does that make sense? There's a couple different transcriptions of these problems. There's convex hull formulations. In something as simple as this example, they're all going to be basically the same. So, okay. So it's easy enough to write that as a mixed integer program. I should say, by the way, that this is the general class of mixed integer programs, okay? If I just say MIP, mixed integer program, that just means I'm minimizing some objective, subject to some constraints. This is just what I've always written for any optimization problem, okay? Except that I'm going to define that some subset of my decision variables are restricted to be either 0 or 1. That's mixed. That's actually a mixed binary plus continuous, but it's actually very hard. Even though everybody calls it mixed integer, it's actually very hard. In fact, I would love to hear it if you ever find an example of someone using the integers more than 0 and 1 in their solver. It's actually really hard. I've not seen a robotics example that was, you know, not super contrived where you could actually use the full integers. Okay, so mixed binary doesn't sound quite as cool. We call it MIP. MBP doesn't roll off the tongue.
You can always write it as a binary.
You could take integers and put it into binary. Yeah, that's right. That's right. For any fixed number of, yeah, that's right. Good. Okay, so that's what I mean by mixed integer programming, is that there's some decision variables that are like this. Okay, so there's particular solvers, just like we see when we've used SNOPT for our non-convex optimization. You'll see that depending on which way you've installed Drake, but probably you see CLIP for linear programs and OSQP for quadratic programs. And if you get second order cone or SDPs, you're going to see Clarabelle these days. On my machine, I always install the powerful commercial solvers, so I'll see Mosec and Garobi most of the time. Okay, Gurobi is the strong mixed integer programming solver, okay? It's actually even though the algorithm, the intuition behind how to write an MIP solver is very simple, getting it to be performant is extremely hard. And the difference between Gurobi's huge bag of optimizations and heuristics and a naive implementation is just very big, okay? So I have Gurobi enabled here. You can do it too if you install Drake with that option. Here's the big M formulation, okay? I can just run basically the same example, but now as I move the initial condition around, it's just able to solve very, very quickly, okay, and avoids the local minima problem, okay, because I explicitly told it there's an OR here. Okay.
What do you do about the case when you may have mentioned this, when the start is directly?
Yeah, it picks. There's two solutions that have the same cost. And the mixed integer program, nope, the mixed integer, that would give us either one, right? So.
Is it random, or is it like it will side with the left side?
So in this particular case, I don't know, I can't think of anything that would cause it to choose one side or the other. Yeah, there's a perfect symmetry there. Everything's zero right up the middle. I think it's just going to pick either one. Yeah. Okay, so how does the solver solve? So by the way, it's mixed integer convex if f and g are convex. That's what MIP is, okay? MICP. We're going to talk about convex relaxations in a second. Okay, so how do you solve? Let's just a mental model of what the solver is doing to solve this. Okay, well, I guess I have to say convex relaxation to understand branch and bound. Okay, so the cool thing about a mixed integer convex problem, if this is convex and this is convex, is that if I take the convex relaxation of this, right? So instead of saying B is either 0 or 1, there's a natural convex relaxation which says B is anywhere between 0 and 1. Okay, that's just the convex relaxation sort of the mixed integer program. And then we're going to say that the convex relaxation is tight when the relaxed solution is a solution to the original problem. So when you're transcribing problems, we do a lot of work to think about the way the transcription looks, okay? And you try to make it the case that if I solve the relaxed version of the problem to optimality with a convex optimization solver, and all of the numbers come out to be either 0 or 1, okay, then you're done. Your convex optimization solver solved the global problem. And so we'd say that the convex relaxation is tight in that case. But in general, this is a much richer class of problems than this, so you can't always expect that. But some things that look combinatorial can be solved with convex optimization. Even when they can't be solved with convex relaxation, the convex relaxation is still super effective, because let's say I solve it and I didn't get an integer solution, but I got variables like 0.9 and 0.4. Okay, there's a couple things that happen there. So first of all, the convex relaxation, because it's a relaxation, that's an important term, right? We actually made the problem easier. Every optimal solution for the original problem that had the strict binaries is still a solution for the relaxed problem. That means the optimal cost can only go down. It also means that the convex relaxation provides a lower bound on the true cost of the problem, okay? Okay, so I solve this convex relaxation, I get a lower bound, and I get some variables that are not quite 0 and 1. Now, a natural thing to do then would be to start taking some guesses. Like probably, if this one was 0.9, then that probably says I'm going to more likely be successful if I go down this branch, and I say, what happens if I add a linear constraint saying that B0 is exactly 1, and then let the rest of the variables be undefined, okay? Then I get another convex problem, okay? And I can also, for completeness, I'll have to check the other one. Every time I solve a convex problem, I've got a lower bound, and I'm going to get increasingly higher lower bounds as I narrow in on the solution. And similarly, whenever I get all the way to the bottom, where I've assigned all of the variables, if I find a solution that is feasible, then I must have found an upper bound. Any solution that I might not have made the right choices here, but anytime I find a feasible solution that has all of the binary variables assigned to either 0 or 1, that is a solution to the original optimization problem, every solution of the optimization problem gives me an upper bound. The cost clearly cannot be more than a solution that I've already found. So the game in branch and bound is to carry around a lower bound and an upper bound and do the most effective search you can using these convex relaxations to go through the tree until the upper bound equals the lower bound, and then you know you're done. That's the mental model of what you should be thinking about in a mixed integer solver. And the essential thing there is that those convex relaxations, when they're tight or nearly tight, can be extremely effective heuristics for that search. So even though these things by nature will grow 2 to the n kind of branches, as soon as you have a lower bound, if I get to this, if I had a lower bound from here that said I know my lower bound is 10, let's say, I know the cost is going to be more than 10, okay, and I get I get an upper bound that's like 12. So if I've gotten here, I've solved this set of problems, and I've got a bracket 10 or 12, okay. If I come here and the lower bound on this branch is 13, then I never have to proceed down that branch. Okay, so carrying the lower and upper bounds allows me to prune massive parts of my tree, and a strong formulation of a mixed integer problem can be solved, even though they're NP hard in general, they can be solved very efficiently. You had a question? That's exactly right. Yeah, so once you've seen 2 bounds meet, you know that you're done. Right? Yes?
Are there
it always works. It might take a long time. It might be inefficient, impractical to solve, because in the worst case, it does have exponential growth, and that's a lot of convex problems to solve, or big problems. Yeah?
Could you explain the pruning again?
Yeah?
It's like, if I continue to go down that branch, I'm only further assigning variables, like the cost will go up further.
Right.
And so I won't get a better lower bound.
That's true. But you get a tighter lower bound. If it's the case that once b is set to 0, then given that decision, the lower bound for the rest of the problem, is higher than an upper bound that I've gotten from a different branch, then this whole thing gets cut. Right? This lower bound, I should say, is conditioned on you making that choice. So once you've made that choice, it might be higher than the original. It's not a lower bound on the original program. It's a conditional on where you are in the branch. That's what I said badly. Yeah, right. So if this problem conditioned on this is worse than my current upper bound on the problem, then I need not proceed further. I've ruled out b equals 0 as a choice. I've seen min-max trees in a couple of settings. It's probably very similar. Yeah, I have to see exactly what version of that is. Yeah. Yeah.
I think min-max trees has a version for alpha-beta pruning.
Yeah. Okay, he says alpha-beta pruning in min-max trees are more similar to this. That sounds consistent, but.
Single player.
Okay. Yes.
Are we adding these constraints for each point along the trajectory? So do you need to do this type of tree for each point?
Exactly. So the naive transcription, which we wrote here, it's worse than that. Let's think about it, right? So for every n, we have, let's say, 4 binary variables, right? So for every or in the or, I've got a binary variable, naively. There's maybe more efficient transcriptions, okay? Yeah, so 4 binaries times n. So you can imagine 2 to that number gets big fast. Good question. You had a question?
Yeah, do we have the results on prudence as a feasible solution? So I think one has to be the
Only once you've found a feasible solution in general. Yeah. But yeah, as soon as you found one, you have a supremum, you have an upper bound. Mm-hmm. Okay, so then let's think about what makes that an effective search, right? We're carrying lower bounds and upper bounds. Okay, so how well does your mixed integer transcription work? Well, roughly it grows with the number of integer variables, which we just said in that case was like 4 times n. Okay, because that's the size of your search tree and effectively then the depth of your tree. Okay, and it also affects, what's affected is the tightness of the relaxation. So if every time you solve a convex relaxation, you almost get b equals 0 or 1, and your cost is almost the original cost, then your pruning heuristics based on lower and upper bounds can rule out a lot more search, and you can converge more quickly. In the extreme, when it's tight, right, the branch and bound will just solve once, it'll realize it's already found an integer feasible solution, and it's done. Okay, but in good transcriptions, you'll see that it takes just a very few steps and can terminate without examining the huge combinatorial tree. And that's what makes these things successful or unsuccessful. The one that we wrote down, unfortunately, which is the one that we've all been, the community has been using for motion planning for a long time, roughly, is bad in both of these objectives. Okay, so the number of integer variables, like we just said, goes up very fast, and in a way that's kind of a false combinatorial complexity. So what do I mean by that? I think you already sort of implied it with your question, right? But it seems like if I've chosen for these points to all be on this set, right? Then for this next point, I really shouldn't have to be comparing all of the other choices, right? The fact that there's locality and constraints here, it should imply that you could you can't independently decide whether this is on every face and this is on every face. They're coupled by their distances and their sequential nature. So really there should be one discrete decision here, but we're writing 4 times capital N. Right? So we've put a false combinatorial complexity in this. And unfortunately, the disjunctive programming formulations often lead to loose relaxations. So the way I show that is I'll just solve the exact same. I wrote the code here, which is you can call new binary variables in mathematical program, the same way you did new continuous variables before, which is why we call new continuous variables new continuous variables, okay? And I solved it first with the convex relaxation equals false, but this time I'll solve it with the convex relaxation equals true. And unfortunately, it's useless, basically. The convex relaxation has sort of no information about the solution because the average, if I'm going to say this face or this face has to be active, then if B is sort of like in the middle, you can basically interpolate and just go right up the middle of your solution. So that's not the best transcription. And you can do it with the convex hull. They all have the same problem. I think the disjunctive constraint formulation of this is fundamentally not that great. For sure, yeah. We'll actually get to that at the end. That's, I think, a really good way to do it. Yep. Yeah, so you can start playing games in efficiency. Like in this problem, you say maybe if every other variable has to be outside, and then, or you could enforce that like these two have to make the same decision, and these two have to make the same decision, right? And then you could try to reduce the number of binary variables like that. You can definitely do things like that. But there's a better transcription. Okay, but in practice, it's not that it will fail, it's just that it will take a long time to solve and you won't be happy with it. Okay, so another piece of background information. When people are solving discrete graph problems, they do use mixed integer programming type tools, but they don't write it like we were writing it. Okay, there's sort of an important classic, if you've taken a class on that it had, kind of your linear programming class, a basic class on optimization, you will know this transcription. Okay, but if I have just a graph search, okay, and I'm just going to try to find a path from the source to the target on some discrete directed graph, and I'll have it weighted, so I'll have the cost Cij, I'll say, is the constant length from node I to node j, and you just want to find the weighted shortest path. Now, of course, you could do Dijkstra's algorithm, or you could do dynamic programming on this. We've already done, okay? But it turns out you can also solve it with optimization if you want. The way you do it is you write the following program. So we're going to put this varphi sort of variable on the edges, okay? And we'll say that if you take that edge, then that binary variable is 1. If you should not take that edge, then the binary variable will be 0. So instead of parameterizing the vertices being outside some constraint, we're saying if you take an edge, we're going to call the binary variable 1. Okay? And then the classic thing that sort of defines, so first of all, the path, of course, is just the sum of all the edges that you had to take. Right? And then the flow constraints basically say at every node, the number of edges coming in has to equal the number of edges coming out. The delta Ti, delta Si is just because the source is an exception. The source needs to have one more going out than going in, and the target needs to have one more going in than going out. That's what these little deltas are. Okay. Now in practice, for shortest path problems, this is the solution, the sum is either going to be 0 or 1. Okay. But since you don't know which one, you can't write 0 or 1. That would be the binary version of the constraint. We're going to just say the sum going in equals the sum going out. Those are the flow constraints. And then if you make this a binary program, you can just say that the fees have to be either 0 or 1. And that's a perfect transcription of the shortest path problem into a linear program. So this is a linear objective, linear constraints. This is so it's a mixed integer linear program, the way I've written it like this. But this is a famous one, and it's known that if you take the relaxation for this, you could say phi is between 0 and 1. Turns out you don't even need the 1, because that's trivially implied by the other constraints, okay? Then this one is known to be tight. So when you solve this, all of the solutions to this are either going to be 0 or 1 on the fees. So this one is the good case. You never have to solve the MIP. You just solve the LP, and you get an integer feasible solution. So that's why it's sort of it's in the lore. It's just shortest path problem is a linear program. Yes.
Is the intuition behind this something along the lines of like, if you have some edges going out of some node, and let's say one of them does belong to the path, which can have lower cost, and one of them doesn't, which can have higher cost. One of them is the weight.
The solutions to the linear program will always be, there is always a solution to the linear program that is 0 or 1 everywhere. So just satisfying all these equations will give you an integer feasible solution. There are cases with perfect symmetries where it's also an optimal solution, where you can go 0.5, 0.5, but in that setting, if you use a simplex method or something, you will always get to the corner, which is sort of 0 or 1, a basic feasible solution. So I don't think you ever get in a situation where there's sort of 0.5, and you have to think about it, or branch and bound. You just solve the straight up problem, and you're going to get good solutions. Okay, so GCS, which you've heard us sort of alluding to a few of you writing your projects about, is just trying to take that version of the problem that works well, This has been a long time collaboration with Pablo Perillo, who teaches optimization classes here. He's fantastic. If you ever want to take a class on optimization, find out when he's teaching it and take that one. Because I was complaining one day about mixed integer problems, formulations for planning through contact, and I'm like, the relaxations are so bad, like we're just doing something wrong. And he said, well, the linear program for the shortest path is tight, so what are you doing wrong? And so, like 3 years of working on this later, we kind of figured out what we were doing wrong, and it's just way better to do it this way. So the question is, how do you leverage the structure of the shortest path problem and use that for motion planning, let's say. But we'll do it in steps. First, just an abstract problem, no motion planning yet. I just got a source and a target, but let's generalize it now so that every time I want to put some continuous decision making in this too, okay? So let's say every time I have a vertex here, I'm going to associate with it some continuous convex set, okay? So there's continuous decision variables, and I get to pick one of them from this set if I visit this vertex. Okay, and the sets can be interesting and arbitrary as long as they're convex. I'm allowed to now have distance functions, which were not, before they were just scalars, right? Constants. Now they're going to be convex functions of the distance, let's say, or some notion of any convex function of those continuous variables. You can also write convex constraints on the vertices or on the edges. I didn't list them here. Okay. So this is the original classic shortest path, is an LP. And we have almost the same problem, okay, where now I just have this somehow convex function times my binaries is the total sum of the costs, okay? And then these xi's have to be drawn from the set associated with the convex set, x associated with vertex I. These are the same, okay? This one, we're going to modify a little bit. Let's think of that for now as phi is either 0 or 1, okay? That gives us a graph of convex sets problem. And it's bad as it looks like this. This looks bad. Like this looks like I've got a convex function, but I'm multiplying it by another thing, so it's bilinear. But it turns out like one of the things that is really important in this line of work is just the observation that if you take any convex function, let's think about it as a convex set. So let's say I've got some set that's convex, okay? And it lives in some coordinate system, x1, x2, let's say, okay? If this is a convex set, then there's another convex set, which is the set that projects that that scales that by a positive number, or non-negative number, let's say, okay, down to 0 or up to infinity. I can make a convex cone out of this if I have some other variable, which in this case is my the ij variable, okay? If this original set was convex, then the perspective of that set is also convex. So even though it looks like a bilinear variable, if we know that's a scalar, which is always non-negative, then we can still think of it as a convex set and work with it that way. Okay, so that's why this thing, even though it looks bad, can be still rewritten as a convex objective function. And it makes things a lot better. Okay, so now the way we're doing it for this sort of simple problem is we have our obstacle, and basically I made a region that's over here, another region that's over here, another region that's over here. Okay, these are my sort of regions, and I just said that I have an initial variable, okay, and I'm gonna have some number of variables in each set, and the edges. The simplest one would be to just do. I'm going to take any 2 points that are in this set. Okay, means that the line segment is in that set. Okay, and then I'm going to have another 2 variables that are in this corner set, another 2 in this corner set, and another 2 in this corner set, okay? And then basically, if I'm going to make a connection, if I'm going to follow the edge between this set and this set, then I have an equality constraint saying that this point and this point must be the same point. If you take the edge, those must be the same point, okay? And similarly, any edge that you possibly could take, it just constrains that those points must be the same. That means you get something that looks kind of like this. You get the source node that transitions into a node at the bottom, one at the left, at the right, at the top. I guess I did a slightly different set of boxes, but it's similarly a way to decompose that, okay? And this time it's closer to the right. It's still more decisions than I wanted. I wanted only one decision, okay? But now I've sort of made a very small number of binary variables on the edges. That's the first point. Do I need to go from the bottom to the left or to the bottom to the right and then back to the top and there, okay? And by virtue of being in this region, I can guarantee that a line segment in that region stays collision free. Now, the reason you need more than one decision is because this region here, the kind of going right, if you parameterize it in the original space, is not a convex set. So I had to break it up a little bit more than that to make sure that I have a mixed integer convex program. Okay, that set of solutions as in the configuration space is a non-convex set. But it's closer to the right thing. Okay, and then, of course, if I run this, that works also. I can move it around. It solves fast. Just notice there's less points. And one of the things I really like is that the number of points in the solution is not pre-specified. Like in all of the other solutions, you chose an n, and it had to satisfy it in that n. Okay, this one also just works. And then if I now, in fact, that was already solving with the convex relaxation equals true. Right? So that was actually doing something that looked like it was the mixed integer version, but that was just solving the convex relaxation. The convex relaxations are tight. Okay, so yeah, please.
How hard is it to create this set?
Yep. So it completely depends on the problem. If you're thinking about it specifically for motion planning around obstacles, then there is a whole game of trying to, so we have a set of tools that work for Cartesian space, that's Iris, and we have a set of tools that work in configuration space. If you have to worry about like collision-free planning in configuration space, that's Iris in configuration space. But we do a lot of work to try to make those sets for collision-free motion planning. There's other problems that GCS solves that are where the sets are just obvious from the transcription. I'll show a couple examples. Mm-hmm. Yeah.
Do you mind going back to the transcription?
Yep.
Sorry, the one where you
Okay.
so the Lij is your like shortest path constraint both on like this graph of convex sets and also like the overall path of
This is the cost of traversing any one edge. So it's a little, in that particular example, so the slightly more general version of that, I'd say that the sum over vertices of some Li of vertex I, okay, plus the sum over edges of Lij xu xv, okay, with the var phi ij, and then you can do, if any one of, you can similarly write this as a, using the same var phis. It's like, it's going to be the sum of outgoing edges. So there's a notion of writing a cost on a vertex also, okay? I just kept it simple on this slide, but in general you can add costs on vertices or costs on edges, constraints on vertices, constraints on edges. So in that particular transcription, the cost is the length of the segment inside one vertex, and the constraints, the edge cost is actually 0, but it constrains that those 2 points must be the same. So this could capture all the vertex constraints, but I would really like to also say, if I write the full version out, I'd also say that for all edges, then xu xv is in some x edge set. So it's true. There's additional costs and I mean, I guess like always when I've been writing the optimization transcriptions, direct collocation, I always write like ... additional constraints. I was thinking of it like that. You can write additional constraints. Once you have these variables flying around, you can add additional costs and constraints.
Sorry, last question.
No, it's good.
The xi and xj, how come those are always what if I want to
Okay, so in this transcription, this is great. You're asking more questions than I expected, which is awesome. Okay, so let's say I've made this region, and I want to identify 2 points that are in this region, which defines a line segment. Okay, then what is my x for this set? Okay, so this I could define as a convex set. It could just be a polytope or whatever. That would define the containment of 1 point. Okay, but in this case, the transcription to the graph of convex sets, the vertex actually has, let's say this is 2 variables. This is also 2 variables. Every vertex has 4 variables. And the set that defines it is actually the Cartesian product of this set with itself. So it's a 4-dimensional set saying that these 2 variables have to live in this triangle and these 2 variables have to live in this triangle.
And then your edge constraint
Uses a subset of the variables, are constrained to be a subset of the variables in the next one. Awesome. Yeah. Yes?
I think you had an example where you had 2 robot arms manipulating the shelf.
That's true. Yes.
Is that done in like the joint configuration space approach?
Yes. That's right. Yep. Yeah. We have one example where it's kind of almost playing Twister with itself, and it's a very complex space, but you can similarly find these regions and solve it nicely. Awesome. Okay. So that solves So I spent a bunch of time this weekend and yesterday and stuff just carving up a bunch of just GCS instances in the code for you, so you could play with this. One of the nice things that I like is that if you take the basic GCS machinery and make all of the sets be points, then you actually get back the original classic LP. Okay, so it's like not worse to go through. I mean, it's maybe a little bit worse in the overhead of the solver, but the solver comes out with the same problem. So if you write a classic shortest path and you add vertices, GCS add vertex, and the vertices that you add, the sets you add are all points. Okay? And then you add edges between vertex 1 and vertex 0, whatever. It's just a random graph. And then it can find the shortest path like that. And that's just an LP. Okay, and then this is the sort of one that's just my quick example of something like what I've been using as a cartoon on the slides. Okay, it defines. Let's just show you a little bit of the mechanics of that, right? So we have vertices that are points. I made a few that are polytopes, a few that are hyperellipsoids. Just kind of made arbitrary convex sets in that picture. Okay, and then minimized the path, and it shows that red path. Now, I solved it twice in this example. I solved the shortest path with the convex relaxation equals true. Okay, and then I solved it again with saying, please do some rounding. Let me tell you what rounding is in a second here, okay? This gives me a feasible solution. And I plotted the relaxation value and the upper bound that I get from the feasible solution, and they're the same. So even though I never solved a mixed integer problem, I know that I found the optimal solution. Yeah, Mike?
That's not a straight line that goes through P5.
Yep. Why is that, right? Why doesn't it go straight? Yeah, it's because it's actually using the squared distance instead of the distance. It's one of the reasons I hate the squared distance. But yeah, it would be easy to change this problem to use the L2 norm. It's actually just because NumPy makes it a little more ugly that I chose this one. Yeah. We're going to get to that. That's an awesome question. He says, what if the graph changes on the fly? So you want to maybe manage this graph on the fly? Yeah, we're going to get to that. Probably not today, actually. But that's a harder version of the problem. Yeah. OK, so what did I mean by the rounding? OK, so imagine I've got this graph. In fact, you could actually even see it in the simple example I did. But imagine I've solved some graph, and these are all, let's say it's a GCS. That's fine. I've got some graph. And my convex relaxation came back, if it comes back with sort of like my binary variables here, I'll just call it B again here, is 0.7, 0.3, right? These are the binaries associated with that edge. Well, then you might need to go in and do branch and bound to figure things out, right? This is going to be 0.3, let's say. But if the branch and, so you could definitely do branch and bound. When you say convex relaxation is false, the GCS will solve with branch and bound, okay? However, if you think your convex relaxation is often tight, okay? And if these numbers are instead coming out as like 0.97 and 0.03, okay, then you're kind of, you're bringing a big hammer to the table to bring the branch and bound to that. It will solve very efficiently. It's a good way to solve the problem. And the other thing is that you kind of know something about the graph structure that the branch and bound doesn't actually know about. So when you talk about rounding, we basically just do some quick search and say, what if I turn this into 1 and take this path? Okay. In fact, the right interpretation is use these binaries as probabilities of flowing through the graph, and you solve the problem given some path that was chosen like this. And if you solve it a handful of times, then you take the best one. That's what I'm getting is the rounded solution. And again, if the rounded solution gives me an upper bound, the convex relaxation gives me a lower bound. If the two are the same, then I'm done. I've found the optimal problem, optimal solution. Okay. That's another super important point about the sort of GCS framework, is that if the path is known, if you specify just a particular path through this, then that implies you got a convex optimization. It's easy. In fact, there's an access in the GCS code that you can just say, I want to solve it on this path, and that'll just solve a convex problem. Okay? If the continuous variables are known, like if you went through an a priori set, I'm going to choose the x values for each of these sets, then that reduces to the original graph search problem, and that problem is also easy and scalable. Right. So in some sense, once we use the convex relaxation to get a pretty good guess, we just alternate through the graph search with a very strong heuristic and the convex problem to quickly find a solution. Okay, yeah. Say it again, multiple paths? A smooth path. So I sort of cartooned decisions that look like that line segment, okay? But the game then becomes what are the richest constraints you can write with convex optimization, right? So I said, I've got an obstacle here. I'm going to make a set like this, and I'm going to define my sets by saying 2 points are here. Okay, but it turns out if you want to parameterize an entire continuous curve, then the way we do it for that is we choose Bezier curves, where Bezier curves are defined by control points, and they have the property that if all of the curve that comes out is completely guaranteed to be in the convex hull of all the control points. So that means by just guaranteeing that the control points are in the triangle, you guarantee the entire curve for all time not even sampled approximation, for all time is inside this. So we write optimizations on Bezier curve parameterizations inside that set. And then you get beautiful smooth trajectories. And then you can put constraints on like the derivatives being smooth at the joints. Things get more complicated if you want to stretch and shrink this thing in time and put acceleration constraints on the knot points. That's where it becomes non-convex. And if I have time, I'll mention that at the end, how we do that. But there's a recipe there where you find the best convex transcription of your problem, okay, and let the convex optimization handle that part, let the discrete part go into the graph search. Okay, it turns out there's a lot of problems we've looked at before that can be transcribed into this sort of GCS framework. So first of all, like choosing a continuous path through a maze, you can find these crazy paths, and in a lot of cases, the convex relaxation is tight. Quadrotors flying through mazes, I wouldn't have thought that would be a convex optimization, but it works out. Good, okay. Remember the first optimization we wrote in trajectory optimization? I just took the double integrator, so linear dynamics, okay? And we made, we wrote the simplest trajectory optimization transcription. Right, we said, I'm going to minimize over x, u, some convex function of x, let's say subject to xn plus 1 equals axn plus b un. In the double integrator, we said it has to be bounded like this, and then we said, for instance, x0 equals 0, or let's say equals x0, and x big N equals x final, which we typically took to be the origin. Okay, you can write LQR objectives. You could write time as the objective. When we wrote time as an objective, we always are solving over a fixed number of n, right? So remember the code? I had to go through and do a line search to find what was the right n in order to find the right solution. If I just said for minimum time, I just set this to 1, or dt, okay? And I had to search up and down n to make that work. Okay, so first of all, anything we wrote there before, you can, if you like, write that as a trivial graph of convex sets. Like there's no interesting graph structure here, it's just a serial chain. But you can write the decision variables here being x, or x and u if you like. I wrote this as the variables here minus the variables here, xn plus 1 minus axn, have to be in the set defined by a bounded u pushed through b, right? So that would be equivalent to writing xn plus 1 minus axn is less than or equal to b times plus 1 b times minus 1. I just wrote it in this notation, okay? But basically, because you can write linear constraints on the edges, you can get exactly the same problem in a GCS framework. And when we're done with all of the optimizations, we're still finding ways to handle all the good cases as optimally as possible. Then you should also just get out the original QP or whatever the original problem should have been. Okay, right now you get something a little bit more expensive, but we'll make that better. Okay, and if you want the minimum time, you just choose L as dt, right? The edge length is just dt. But what GCS can do, or these kind of graph sort of structures, is I could do one more step here. I can, for instance, I forgot to say I should just take the source and make that an equality constraint here is a simple way to do it. Okay. And of course, at the end, I can transition with a constraint saying that the x's here are basically 0. But I can allow prematurely transitioning to the target if the value here gets to 0. Right? That's just a way to transcribe the variable time horizon problem into a graph of convex sets. So first of all, LQR works as a graph of convex sets, and then minimum time linear optimal control works as a graph of convex sets. And I coded that up just to, so you guys have all these available to you. I forgot to open it. Min time GCS is now at the bottom of the double integrator notebook. And I get to solve convex relaxation equals false because I have the solver and it does beautiful things. Yeah? This one, the convex relaxation wasn't always. If I make this true, which is the only thing I'm allowed to put on deep note basically, because you guys don't have the solvers by default. It does pretty well, but it's actually not tight. It's close. And I found some time horizons where it's worse even. So I know I'm going to be spending this weekend figuring out why that's not completely tight. I already spent most of last weekend trying to think about it. Okay. So that's cool. We can take some of the trajectory optimization. So far we did linear optimal control with convex optimization, but now we can do variable time step linear optimal control with an extension within GCS. Similarly, we can do piecewise affine optimal control. So the essential piece being here that it's piecewise, okay? Imagine I have some domain, x1, x2, that I've carved up here. And let's say that the dynamics of my system are different in different pieces of the domain. So let's say I have, I don't know, some sets in my domain, okay, and when I'm in this set, my dynamics are xn plus 1 equals a1 xn plus b1 un. I can even handle the c1, that's fine. And over here, this is a2, b2, c2, right? a3, a4, a5, a6, a7. You get my point? So if I'm solving optimization problems with an initial condition over here and a final condition over here, I might need to go through different regions in order to subject to different dynamics based on the location of my set. It turns out this is a good way to think about contact in some cases, because when you're in contact, you have a different dynamics than when you're out of contact. Now, in contact, you're not often, this is a nice case where the sets are polytopic and the dynamics are linear. Often contact, you get curves and different nonlinear dynamics, but this is a reasonable approximation of contact. And there's many other places where piecewise affine systems come up. Okay? You can transcribe this also as a GCS, where now you say, it's basically the same picture I had on the board a minute ago, right? I'm going to make roughly my dynamics here with the edge constraints enforcing the dynamics, right? But I'm going to make a copy. I'm going to make a vertex. This is the naive transcription. I think there's probably better ones depending on your specific structure, but this already works, okay? Basically, I'm going to say that this is corresponding to mode 1, mode 2, mode 3, mode 4, and the GCS is allowed to choose a path through the graph. So you get what I'm doing here, yeah? It could be fully connected. Maybe you could do some pre-processing if you know it's impossible to jump from 4 to 1. okay? And then again, you have your source here, which you can make edges to there, which can only be taken if if the equality constraint puts you in that initial set, for instance, and similarly on the target. And this isn't always tight, but I think it's the best transcription I know of for the piecewise affine MPC, if you will, the extension of the linear optimal control MPC to piecewise affine. This gives tighter relaxations and faster branch and bound than the other transcriptions, partly because the other transcriptions were all horrible. And this gives better ones. Okay, and in practice, when you start playing with curves and everything and other dynamics, there's ways to do better still. But this, if you want to just lock yourself in time and do the dynamics with piecewise affine, this is a way to go. Okay, got a whole bunch of examples. So if I had had another 2 hours before lecture, I would have, you can use this exactly. Like, remember the basketball bounce pass, where I had to solve n different problems, one with 0 bounces, one with 1 bounce, one with 2 bounces? That would be perfectly encoded as a piecewise affine system. And you can do planning through contact, where it decides the number of bounces exactly with the piecewise affine transcription. There's actually another good one that we did a few years ago that I'm going to bring back in the notes. This is Robin Dietz, who did a lot of our early mixed integer planning. He, on a weekend, coded up juggling, and it's linear because the dynamics of the balls are linear in the air. Okay, so it's mixed. It's a piecewise affine kind of system, and you can solve these, hard combinatorial. What do you do with your hands? Juggling problems with it. Okay, so I know some of you care about quadrotors and the like. So let me do that in a few steps. So let's say you want to use this for quadrotors. Step 1 is what's the best convex formulation for planning trajectories of quadrotors. And that came from this differential flatness work. This was from UPenn. They showed these awesome, high-performance trajectories of the quadrotor in tight sort of obstacles, okay? All using convex optimization at the time. Okay, and even
we implemented an autonomous controller capable of recovering from extreme initial conditions.
There's a piece here that I just love. There we go. Oh, no, he's got one where he throws the hula hoop. There we go. Whew. Okay, that's awesome. All right, so that works incredibly well. Okay, that's called minimum snap. Trajectories for a quadrotor. It's in the notes. How does it fit in? Okay, so this is effectively choosing a mode sequence. Okay, so for every step in n, they are restricting n to be inside a convex set. So they picked some n and said n has to be inside the hula hoop at some future n. Okay, and in that space, the transcriptions that they wrote are like the best sort of transcriptions we have for convex optimization of those trajectories, right? Every x n is got to be in some convex set, as opposed to being able to choose which convex set at which time, which is the harder mode sequence problem. Okay, and they also had to choose the time horizon, which is a little bit of a funny thing because you're trying to do minimum snap, kind of minimum time trajectories, let's say, but you have to pick the time horizons you're planning. It's fast enough that they can do it online in receding horizon, and that wasn't a big limitation. But if you wanted to plan all the way from the start to the goal, it's hard to know what the time it's going to take to get to the goal. Okay, so They did work with the old transcription, the one that's not very tight, that extended that work to flying around obstacles. Now we can do the same thing with GCS, and just it solves a lot faster. And that's like actually, sad face. Okay, here we go. Do I dare? Testing fate. I'm plugged in, so that was not a crazy thing to do. See, maybe it was better. Okay, well, I've also linked it from the notes. You can solve, you'll see like teams of quadrotors flying through buildings, okay, using the Mellinger minimum snap trajectory sort of transcription, plus the GCS to make the decisions about where you're going, left or right. Okay, so this is a manual decomposition of the space. We know that these are boxes. We made some decomposition manually, okay, even in the procedural sort of, we made a bunch of different houses, but it was easy to sort of cut out the boxes for the different regions, okay? And you can choose whether you want minimum distance or minimum time, and sometimes with the dynamics of the quadrotor, you can get different paths. But you can solve these things nicely to global optimality. Statistically, it's almost always tight. The relaxation often gives you the true optimal solution. But it's not guaranteed to be tight. Okay, now there's a couple subtleties here. So in the first GCS paper that we did, we have a GCS motion planning paper. We call it GCS TrajOpt. The snap constraints, actually even velocity, acceleration, jerk, snap. You know minimum snap? So snap is, these are the derivatives of position. Position, velocity, acceleration, jerk, snap. These are going higher derivatives. You know what the next two are? Good, good, good. Yeah, it's true. That's like hardcore physics, yeah? Okay, so it turns out that in the parameterization where you've put Bezier curves, and you have time as a decision variable because you don't know how much time it should take to go through each region, then velocity, acceleration, jerk, and snap become non-convex constraints. Okay, so in the original GCS trajectory optimization, we just used convex heuristics to push that down, and with some success. In this newer version and the newer GCS code, you can actually put you can specify in GCS non-convex constraints that will only be used during the rounding step. So it's exactly what, I think one of you said this exact, oh no, that was, you said, should I use GCS to do the coarse approximation and then you add nonlinear constraints at the end? That's exactly what's happening here. And we try to make surrogates or approximations of the true non-convexity in the original optimization so that GCS guides its way through the solution to the right, use GCS to get the global optimization, and then we round it with nonlinear optimization to handle the non-convex constraints. Okay. Footstep planning. I know some of you are playing with footstep planning in GCS. Okay. So footstep planning, when I talked about it last time, I said that there's a recipe that comes directly out of the ZMP world. Okay. Where we broke it down into 3 steps. You plan your footsteps, typically with heuristics, okay? You plan your center of mass and center of pressure. ZMP trajectory. And then you plan your whole body. Right? And this is the decomposition that has been pretty good, okay, for Asimov walking around office spaces and the like. But when the terrain gets more complicated, your footstep planner needs to get smarter. And at some point, if you do have constraints on your center of mass and center of pressure, those can affect what footsteps are feasible. So what we've been doing more recently is trying to basically solve these jointly. Where the MIP formulation captures the footsteps, and then the center of mass, center of pressure trajectories become linear dynamic constraints using the ZMP equations, okay? And so we're able to now sort of jointly solve for center of mass, center of pressure, and footsteps. And that's where you get these kind of solutions like the humanoid walking around obstacles. If you remove the stepping stones, then it figures out it has to take a different, fundamentally different path in order to walk around. And Atlas walking through the door, you know, like Hans and Franz, and these are the footsteps making discrete decisions. This one wasn't absolutely tight, but just to give an example, the previous best formulations, if you solve the convex relaxation, you look at the cost, how close is the cost to the optimal solution for the MIP? It was getting 7% of the MIP solution, and now the convex relaxation gets 80%, for instance, in that case. And it might even probably, since we did those numbers, we've probably strengthened a few things and made it better. Okay, this is, can you guess what this is? Taken out of context, it looks hilarious. It's a humanoid whose dynamics are a box that's not allowed to rotate in this simple example, and its hands and feet are points. Yeah? It's not Atlas driving. It's Atlas doing push recovery. So we wanted to have the case where if Atlas got pushed, okay, and there's a wall nearby, then it would, you know, for small pushes, it would go like this. For big pushes, it would actually put its hand out, push, and go like this. So in the case where we linearized the dynamics away, and we abstracted away the dynamics of the arm or the kinematics of the arm into points, we just put sort of rough kinematic constraints. This is a lot like footstep planning, but it's now up in the vertical plane here. Okay, then we can solve these with mixed integer optimization in a similar way. And then, in both of those cases, actually, we've said that the dynamics of the center of mass are linear. But as soon as you start rotating or allowing angular momentum, in the footstep planning case, we assumed it was linear because we assume we have a low-level controller that's regulating the body angle and the angular momentum. Okay. In this case, it's a little bit more sketch. But as soon as you start putting orientations in, you have to do something else to deal with the non-convexity that comes from that. And the general recipe here is find the tightest convex relaxation you can for all the ugly nonlinear constraints, use that to guide the search, and then tighten it in the rounding stage with nonlinear optimization. And we've done that over the years with a series of different things. This is little dog bounding, okay, which is solved, again, with a mixed integer convex optimization. This was before we had GCS, so we just waited a long time for it. And the way it worked is that we would partition the space into aerial phases and ground phases, right? And we just broke up the space, made our graphs, and then we put bounds on all of the angular momentum type terms, right? And we could solve that to optimality. Now, when we were doing that, I remember Andres, who did that work for his thesis, I mean, he had to be a little patient on the solve times, but he was like, it is so rewarding to be able to have an optimization that's solving problems like this. And when it's done, it either says, yes, here's the optimal solution, or no, the problem is infeasible, right? The whole thing where like SNOP got stuck is super frustrating. If you do that, you know, it's like hyperparameter tuning or something. It's just like, you know, you don't want to do that. I mean, but we didn't even have like WANDB and other tools back then. So this was just a very different place to be in. And that's what we're trying to get more and more at. My goal for under-actuated in, like, I don't know, this decade is that nobody ever calls SNOPed. And they just, every problem you ever want, we just have a solution that works and says yes or no. And it'll be a happier time. Yeah. Okay, I'm out of time, but there's a bunch of other things we can do with it. We can plan through contact a bit, you know, and this is some of the kinematic trajectory optimization. Works really well. But that, in these cases, then you start getting into the hard question about how do you find the sets. Yeah. And that'll be more naturally discussed after we talk about the sample-based planning. Cool, okay. Oh, snap.